Okay, so this is our lesson 15.3. We're talking about tangents and circumscribed angles. And before we talk about those, there's some new vocabulary there, but there's also some old vocabulary. So let's review a few things. All right, so remember there are a few segments related to circles that you need to know. There's the radius that goes from the center to a point on the circle. There's a diameter that goes through the center from between 2 points on the circle. And then there's a chord that goes to 2 points on the circle, except it doesn't go through the center. I remember all those are segments because they have endpoints. So today we're also going to talk about a different type of line, which is called a line of tangency. And you've heard the word tangent before when we talked about trig, but tangent lines, so first of all, it's a line, which means it's going to have arrows. Tangent lines mean they just hit the circle in exactly one place. All right, so this picture is not super great, but the idea is that you're just touching the circle in one place. Think about a ball sitting on a table. The single point where the ball is touching the table, that's a point of tangency. All right, and then a few other things that we need to review are about angles. So far about angles, we know some things about central angles. Remember, central angles come from the center. They have a vertex on the center. And then we learned about inscribed angles, which have a vertex on the inside of the, or on the circle rather. So remember, inscribed, even when we talked about triangles and circles, inscribed is where the shape or the figure that you're talking about is inside the circle. Circumscribed is the shape outside the circle. So for example, we can circumscribe an angle, which means to put the angle on the outside of the circle. Ooh, need to change that point. All right, so the idea here is that this blue angle is called a circumscribed angle because the angle is outside of the circle. Okay, so there are two theorems that we have to talk about today, and the first one I want to pull on something that we've talked about before, and that is when we inscribe circles in triangles. So remember, here is where we wanted the circle to be equidistant from the edges, so we did that by using the angle bisectors. And what we do is we find this point in the middle. Now remember, this is equidistant from the sides, so if I draw a distance to the sides, it's going to be equal all the way around. So two things. One, remember any of these distances I draw from the center to the edge are all going to be radii, which is why they're all going to be equal because they're in the same circle. And then the other thing I want you to think about is how do you measure distance? And we've talked about this before, that you measure distance perpendicularly, which means this radius to this line that we've drawn on the outside are all going to be perpendicular because we're measuring perpendicular distances. Remember, that's true all the way around. So we have a new theorem today, and what it's going to say is that this line that you drew, you didn't know this when you were drawing it, but this is a tangent line, right? It's only touching the circle in one point right here on the outside. And a tangent line is always going to be perpendicular to a radius. So there's our first theorem that we're going to end up using today. Okay, so here's the second theorem that I want to show you today. And this has to do with when you have two, two tangent lines on the outside of a circle and how they're related. So we just learned that if we draw the radii between both of these, that we're going to create 90-degree angles. So we know that both of those are perpendicular. Here, and I'll draw that 90 on this side. You'll see why in a minute. And I want to talk about what's the relationship between these two tangent segments. So one of the things I can do here is I can draw a line from the center to this outside point, and that's going to create two triangles. And some things that you should know now is that those angles are congruent. Those sides, those two radii, and obviously this middle section is going to be congruent to itself because of reflexive. So then that is going to lead us to say that these last two tangent segments are going to be congruent because if you see in this picture, and you can kind of remember back, this is going to be an example of HL. Remember, we can't do angle, side. Angle, side. That's not a reason, but because this is a right triangle, we can use HL. So with that, we can say that the two triangles are congruent, so then the two tangent segments are also going to be congruent. When I refer to this, I often refer to it as like the ice cream cone theorem, which is not a real thing. But I do that because if you think about it, we've got two sides of the ice cream cone that need to be equal to fit the ice cream inside of it. Also, ice cream is fun, so why not make geometry about ice cream? Okay, and this last theorem, I'm going to let our book kind of walk us through it because it does a good job. So it says angle AXB is circumscribed angle of circle C. So that just means that these are points of tangent C, A, and B here. So since they are circumscribed, then XA and XB are both tangent to the circle. That's just by definition. Therefore, XAC and XBC are both right angles, right? We know that because they're tangent and those are radii, then those are both going to be right angles. All right, and then they're saying in this quadrilateral, the sum of the measures of 4 angles, well, I've got 4 angles, so I know that means they're going to add to be 360. Even if I don't know anything about them, I just know their sum is 360. All right, so since XAC and XBC, the addition of those is going to equal 180, right? 90 plus 90 is 180. Then that means for this additional problem that AXB and ACB is equal to 360. All right, so let's see which ones they're talking about. AXB and ACB is equal to 360. That's all of the angles added together. Minus 180, that's these two right angles that I know, is going to equal 180. All right, so what that is going to lead us to say is that then those two angles are going to be supplementary by, this is just substitution because all I'm doing is subtracting. All right, so the big thing that you need to see there is that those two angles, the theorem we're trying to find, those two angles are supplementary. So we're going to write down our third theorem and last one for the day is to say that a circumscribed angle and its corresponding central angle are going to be supplementary. So no matter where or how we draw this, however far we pull x back or however close we push it, this exterior circumscribed angle and the corresponding interior central angle are going to be supplementary, which means they're going to add to equal 180.